In this video, let us find the area between the two curves. Suppose if R is a region between two curves, we can find what is the value of R. Let's take two curves. One, the blue one as f of x and the red one as y is equal to g of x. We are interested in finding this shaded region between the two curves, that is the area between the two curves f of x and g of x. And the formula to calculate the area is the integral a through b f of x minus g of x dx. That is, the integral from a through b of the curve on top minus the curve which is down below. Upper function minus lower function of dx. Here x ranges from this point a to b. As we move the slide, this line varies from a through b. If we want to cover this whole region, x varies from a through b. Suppose if I have two curves like this, so this one is x is f of y and x is g of y. Then this shaded region will be the area of the integral, which is my right function first minus the left function, that is the blue one minus the red one. The blue one is f of y minus g of y dy. So when we write f of y minus g of y, it means that there is a parenthesis here, even if the parenthesis is missing. Remember that it is c to d, or f of y minus g of y, this whole function, which is the difference function with respect to y. Let's take an example here. We have got two functions f of x equal to 3x cubed minus x squared minus 10x, and g of x is equal to x squared plus 2x. So one curve is the red one, the other one is the blue one. We are interested in finding the area between the two curves. So it looks like there are two regions. In this region, the red curve is above the blue one. But from this region to this region, the blue one is on top and the red one comes below. So we are splitting into the two integrals here. So we have to split this whole thing into two integrals, because in one region it becomes positive and in the other region it becomes negative. So between the first one, say I think negative 2 to 0, the red one is on top. Between 0 to the other one, blue one is on top. So when we write integral negative 2 to 0, f of x minus g of x dx, plus the other one is from 0 to 2, g of x minus f of x, and get the answer A as 24. So we have to be careful when we are evaluating this type of integrals. We have to see which one comes on top and which one comes below. So you can split this into two different integrals like this. Here we are interested in finding the area between the two curves. The blue one is y equal to 4x plus 16, and the red one is y equal to 2x squared plus 10. The first one is a linear straight line, the other one is a parabola, 2x squared plus 10. But when we see the diagram, if we are interested in finding the area when x ranges from negative 2 to 5, we can split this into three, where the first one is from negative 2 to negative 1, second one is from negative 1 to 3, and the third one is from 3 to 5. In my first set from negative 1 to negative 1, sorry, negative 2 to negative 1, the red curve is on top, the blue one is down below. The second set, blue is on top, red comes below. Again, the red goes on top and blue comes down below. So we have to split this into three different integrals. So when you split that, negative 2 to negative 1, negative 1 to 3, 3 to 5, we can evaluate the integral and get the answer as 142 divided by 3. In this example, we have two curves, one represented as x equal to half y squared minus 3, the other one is y equal to x minus 1 or x equal to y plus 1. So the one what you see on your right hand side is the same curve, but it is written in terms of y. You can do this problem in two different methods. Maybe if I'm taking the first diagram, it looks like my blue one is lying to the right of it and the red one comes to the left of it. So I can make use of the second formula, integral over y, where x is equal to f of y is my blue one and x is equal to g of my y is my red one. So f of y minus g of y dy, and the value for y varying from whatever is the lower limit and the upper limit. Or if we are converting all these two equations in terms of y, which we see on the right hand side of the second diagram there, the same curve can be represented as the red one is y. Instead of saying x equal to half y squared minus 3, we have y is square root of 2x plus 6. The blue one, instead of saying y equals x minus 1 or x equal to y plus 1, I have the same line y is equal to square x minus 1. Now this can also be done. You can find the area between the two curves by taking area of the curve above the curve which is lying above and minus the curve lying below, like the one what we did in the beginning. But there is an issue. See, if we are splitting this into two, between negative 3 to negative 1, when I see, the curve which is on top is the same as the curve which is down below, the red one. But when you're talking about the y coordinate, it can be split into two different curves. That's why I have shaded that one as red, the other one as green. See, in the upper half plane, your y will be positive square root of 2x plus 6. And in the lower plane, your y will be negative square root of 2x plus 6. So we can treat this as two different curves. The curve lying above is positive square root of 2x plus 6. The curve that lying below will be negative square root of 2x plus 6. That is the case between negative 3 to negative 1. Between negative 1 to the other one, 4 or 5, whatever it is, you have the red one on top, blue one lying below. So you can add them together. You can add these two values together and get what that value is. So this one will be the area for the one which is on top is red, that top curve is red, the lower one is green. And for this area, the top one is red, the lower one is blue. So if you are integrating that with respect to x, you will be splitting this into two different integrals, one between negative 3 to negative 1, the other one between negative 1 to 5, and you will get the answer as 18. The same thing if you are interested in trying to integrate with respect to y by taking g of y, f of y, whatever it is, with the variation for y, again you'll end up getting the same answer, 18. Whichever is convenient, you can pick. So in this diagram, in this video, we were learning different methods of calculating the area of the region between two given curves. Maybe we'll think about the curve which lies above, lies below, or we can even talk about the curve which is lying to the right of it, left of it. But whichever method we are doing, we have to be very careful whether this is retained throughout. Sometimes in certain region the curve will be above, the curve will be below will be switched when it may flip. The one which was down below may go to curve when it is a movable curve, then definitely the region of integration must be viewed carefully, whether it is with respect to x or with respect to y. Hope this video was helpful in understanding how to find the area of a region between two curves. Thank you for listening and thank you for watching.